Hello everyone. So today we'll be solving two more problems from Irodov as usual, and I've written down the problem. I'll explain it to you simultaneously. I have a small disk A, which is placed on an inclined plane, which forms an angle of alpha with the horizontal, and it is imparted an initial velocity v0. Find how the velocity of the disk depends on the angle phi if the frictional coefficient k is equal to tan of alpha, and at the initial moment the phi naught was equal to pi by 2. Okay, so let me draw the diagram. You'll get to know what exactly this problem is saying. So in this problem I have an inclined plane which makes an angle alpha. So I'm drawing the inclined plane right now. This is my inclined plane. I'm trying to draw a 3D view of the inclined plane. This is the slant surface, and with the horizontal it makes an angle of alpha. This inclined plane has a frictional coefficient k, which is given to me as tan of alpha. Okay, I had a small body, a disk in this case. Initially this disk was impartant a velocity v0. Okay, so this is the direction of the inclination. Okay, and let's say at a particular point its velocity is v. So the angle between the direction of incline versus the velocity is actually given to me as phi. Initially this body was given a velocity v0 in a direction wherein phi naught was equal to pi by 2. Okay, so this is what my initial direction was, and after some time, as this body was falling, okay, as this body was falling, it must have gotten a velocity of v, and at this point it was, let's say, making an angle of phi. Okay, this is what this problem is saying. Okay. Yeah, so there are a few things which I'll have to observe in this problem. If I look at this disk, there is weight acting downwards, which a component of which is being normalized by the normal force, which is acting on this disk by or because of the inclined plane. So if I draw the disk from the lateral view, it would look something like this, right? It has weight acting downwards. There is this component, then there is this component of the weight. This component is being balanced by the normal force. Okay, what is the normal force then? It's nothing else but mg sine of alpha, right? Okay, and sorry, mg cos of alpha, and this force is nothing else but mg sine of alpha. Okay, there are other forces acting on this body as well. That force will be the frictional force, which is going to act opposite to the direction of the velocity. Okay, so if I look at this body from the top, that would give me the best view of what exactly is happening. By the way, please note that this was the initial velocity, and this basically is denoting the angle that the velocity vector is making with the inclination angle. Okay, or with the direction that is directed towards this slope of the inclined plane. Okay, so let me draw the top view. It would be something like this, wherein, let's say, the body has a velocity v. It, with the inclined plane, it makes an angle of phi. Okay, in this same direction there is force which is equal to mg sine of alpha acting in this direction. there is some frictional force which is going to act in the direction opposite to my velocity vector, okay, and its magnitude will be equal to k times the normal force, right? I hope you are getting this. This is the normal force. The frictional force will be directed in a direction which is against or opposite to the velocity vector. So it will be acting in this direction on the plane of the inclined plane. So there can be some inclination or some angle with this particular direction, right? So this is what I've pointed my direction of the frictional force as. It lies on the inclined plane, but it is not necessarily directed opposite to the incline. It is directed opposite to the velocity vector. That is something that you'll have to note. So this angle also becomes equal to phi. What is its magnitude? K times n, right? What is the value of n? Mg cos of alpha. So tan of alpha, which is k, times mg cos of alpha. I can see that cos of alpha is getting cancelled. Okay, so this essentially can be written as mg sine of alpha. Okay, all right. Let me, like, this is the basic force diagram for this disk, okay, or the body. Now this body is going to have two velocities, let's say, okay, and both those velocities are going to change under the influence of the forces acting in those directions, okay. So let's say this be the direction of one of the velocities, or let's consider the acceleration, okay. The velocities are going to change, therefore I'll consider the acceleration, and this acceleration is going to kind of represent the effect that these two forces are having on the velocity in this particular direction. The second acceleration that we can talk about is AT, okay. Alright, this AX is the acceleration in this direction, okay, that is along the incline, okay, and this AT is the acceleration of the body along the velocity vector, and AT's direction keeps on changing, okay. Alright, so AX is something which is a result of the forces which were acting in the x direction, right? So AX times m, this is the net force acting in the x direction. What is this net force? Mg sine of alpha, right, minus mg sine of alpha into cos of phi, okay. So this can be written as mg sine of alpha into 1 minus cos of phi, okay. Let's see that this is my equation 1. Now let's talk about AT, okay. So MAT, which is going to be the net force in this direction, right? This is going to be equal to mg sine of alpha into cos of phi, okay, minus mg sine of alpha. So this effectively can be written as mg sine of alpha into cos of phi minus 1, okay. This is nothing else but minus of this, right? This can be written as minus mg sine of alpha into 1 minus cos of phi. This is nothing else but minus max. Okay. I hope you are getting this. Okay. Therefore, max minus max is nothing else but mat. Mat is equal to minus max. Okay. This implies at is equal to minus ax. Okay. This implies dvt upon dt is equal to minus dvx upon dt. Okay. If I integrate on both these sides, I obviously get dt cancelled. Okay. And after that I should be integrating. So I get Vt is equal to minus Vx plus some constant. Okay. Now, what was the value of Vx when Vt was equal to V0? Okay. Initially, when this body was thrown in a direction perpendicular to the incline, Vx was equal to 0, right? So from that I get the value of C. Okay. Vx was equal to 0 when Vt was equal to V0 plus C, which implies C equal to V0. So this gives me Vt as minus Vx plus V0. Okay. Now, note a few things. Vt is actually the resultant, okay, of two components of velocities. One is Vx, the second one would be Vy. Initially Vt is towards Vy. By Vy I mean the direction which is perpendicular to the incline on the surface of the inclined plane. Okay. So essentially this direction is Vy and this was Vx. At any point of time, let's say this is my Vt, okay, the actual velocity. This actual velocity has got two components, one is Vx and one is Vy. I've got the relationship between Vt and Vx. Please also note that phi is the angle between Vt and Vx. So if I use that, I can write Vx is nothing else but Vt cos of phi, right? And what do I need to find out? I need to find out Vt, right? Therefore, I can write Vt is equal to minus Vt cos of phi. I'm just writing Vx as Vt cos of phi, okay, plus V0. This gives me Vt as V0 by 1 plus cos of phi. This is what my Vt is going to be, and this is what the velocity of the disk is going to be. Okay. As my angle phi changes. Okay. So this is what my first problem was. It is more mathematical than, you know, I mean, you have to think more in terms of mathematics because you have to develop all these relations. The main thing was FBD. Had you drawn the FBD properly, then post that you would have to analyze AT and AX properly, and that is one idea which is more mathematical, I would say. I mean, it has got some physical relevance, but it is more mathematical. Okay. So yeah, this was the first problem. Let's move to the second problem now. Okay. So in this problem, I have a sleeve A that can slide freely along a smooth rod bent in the shape of a half circle of radius r. The system is set in rotation with a constant angular velocity omega about a vertical axis o dash. Find the angle theta corresponding to the steady position of the sleeve. Okay, so essentially I have a semicircular, what is it, semicircular rod, okay, and I have a sleeve, okay. Now this rod can rotate freely about an axis which I am denoting as o dash, and I have a sleeve, okay, which can rotate on this rod freely. Initially this sleeve would have been here, so if I consider this position, like this is one of the positions which is stable, okay, I mean wherein the sleeve can stay, and you know there won't be any effect of rotation on this body, since the radius would be equal to 0. There won't be any need of centripetal force. So the normal force which the rod is going to apply is going to balance the weight of the sleeve as well. Once the rotation starts, this is one of the positions which is stable, okay. Now if I talk about any other position, there is one more position wherein the sleeve can be stable, okay, and that is what I am expected to find out, okay. So this rod is essentially rotated with an angular velocity of omega about the vertical axis o dash. I need to find out the theta, that is the angle corresponding to the steady position of the sleeve, okay. So let's say this is my position and the angle made with this axis of rotation, that is o dash, is equal to theta. If I draw the FBD, there is weight acting downwards, okay. Let's say that the mass of the sleeve is m. There is some normal force by the sleeve, right? And there is a component of this normal force which is actually providing the centripetal force, okay. Now if this angle is theta, what's going to be the radius of the circular path in which this sleeve is going to move, okay. This rod is about to rotate, right? After some time it would reach this position wherein the sleeve would be somewhere here. So essentially this sleeve is rotated in a circular path, right, of radius. What will the radius be? It will be this value, right? What is this value? Let's say its radius is r, the rod's the half circle's radius is r, that has been given to me. So this becomes equal to r sine of theta, okay. These are the two forces which are acting on the sleeve. The sleeve is going to be in equilibrium in the vertical direction. In the horizontal direction, there is going to be some centripetal force which is going to force the sleeve to move in a circular path of radius r sine of theta, okay. So if I write my equations in the vertical direction, I'll get n, what is this angle going to be? This angle is going to be theta. N cos of theta is equal to mg, right, which gives me n as mg by cos of theta, okay. In the horizontal direction, I'll have just one component of n, right? It will be nothing else but n sine of theta, and this component of N is actually providing the centripetal force to the sleeve so that it moves in a circular path of radius r sine of theta. Okay, so N sine of theta is going to be equal to m times omega square, okay, times the radius, that is r sine of theta. Sine of theta gets cancelled. N was equal to mg by cos theta, right? So I put in that value, mg by cos of theta is equal to m omega square r. M gets cancelled. I get cos of theta as g by omega square r, which gives me theta as cos inverse g by omega square r. Yeah, so this is what my theta is going to be. Let me check the answer. Yeah, so this is what my theta is going to be, and this is going to be one of the stable positions for my sleeve. This position is also going to be stable, okay, but yeah, I mean, this is going to be one of the options, but this is also going to be one of the options of the stable positions, right? So yeah, so these are the two problems that we solved today. We'll probably come up with more problems in the next class. All right, bye.